All right, today we're going to start with our chapter 8, which is vectors, and I'm going to do an introduction to what vectors are. And if you have a chance, go into YouTube, and here's a link, and I know you can't click on this here, but if you either type this in or if you just search Despicable Me and Vector, Vector, you'll get a fun little explanation of what this character in this movie is a vector. And he really kind of goes on to explain that what a vector is, and he calls himself Vector, is because he wants to go and do evil, and he has direction and magnitude. And he's very excited about both things. So what is magnitude and direction? And he says, okay, this is represented by arrows, and then we're talking about these arrows. A magnitude here is a force, that we're talking about a force that we're looking at. It's shown by a length or a distance is really how we show magnitude of force. But distance isn't necessarily a force, it's just kind of how we show force. It's hard to show force in a two-dimensional way. Direction, we're thinking about where are we in space. So we might be talking about our Cartesian coordinate system, or what we're going to be talking about, I want you to kind of think we're talking about angle measures here. So a lot of times we're going to be talking about an angle measure. All right. Also, when we're talking about direction, we're also going to be dealing with north, south, east, and west. Okay. So we're also going to be dealing with those types of directions. But before we get into that, let's talk about here just what do we have when we're talking about vectors. Now, if you notice here, this vector symbol at the top, I'm going to kind of point something out. We have a little thing different between this, all right, versus this. Oh, that's a bad one. All right, so an arrow like that versus an arrow like that. This arrow actually indicates direction. When it's kind of shaded in, it's indicating a direction. This is indicating a line that goes on forever. So because this is a vector, we're using this little indicator here that it's a vector, not a direction, and that it doesn't go on forever. This one, it's saying this one goes on forever, and it's a line, and lines go on forever. Vectors has a direction, and that's what the arrow is for, but it has a start and end. So it's kind of more like a segment in that respect, okay? So even though I know there's an arrow on both sides, see this as a start and the end. So the distance of it or the length of it is true to the magnitude. So the fact that here A and B have the same direction and they have different magnitudes, all right, in this first example. In the second example here, A and B are the exact same magnitude, they're exact same length, but they definitely have different directions. So again, they are not equal. Here, in the third one, finally, they have the same magnitude, the same exact length, and they go in the same direction. So that's when, yep, they are equal. Some notations that we're going to be using. We use this little half arrow on the top. So that might be another vector right there, that little C. Also, if we want to say we want to find the magnitude of something, we put it in absolute values. That's usually a common one that we use, absolute values, to show that we're talking about magnitude. And then later on, we kind of use these Pac-Man symbols, I guess, to show an ordered pair. And so we'll be talking about why ordered pair is used to find direction more in our next video, or ordered triple. But in this video, just know that these Pac-Man kind of symbol type of things indicates as one of the notations we're going to be using when it comes to vectors as well. All right, so we have equal vectors. We have vectors that are going in the same direction or have the same magnitude. One that we want to talk about is opposite vectors. Basically, opposite vectors have to have exact opposite, or 180-degree opposite directions. And then they're going to be opposite vectors. In order for two parallel vectors to be parallel, they have to be going in the same direction. All right, so they're going in the same direction, but they don't necessarily have to be the same length, or in other words, have the same magnitude. So we're going to be showing the sum of two vectors. Let's say we have two things, and you're both pulling on the same chair that's on wheels, a chair on wheels. And I'm going to be pulling in this direction, and my best friend Molly is going to be pulling in this direction. And she's pulling a little harder. She really wants that chair to move more than I do, just by a little bit more. So we're pulling in opposite directions. Which direction do you think the chair is going to go? Well, if we're both pulling on it and we're going not in opposite directions, I misspoke, but in different directions, the chair is actually going to go kind of like this, all right? And the way that we go, and this is kind of like an estimation of where the chair is going. And I kind of have an arrow like that's the direction, but we don't know exactly how long. Actually, you can decide exactly how long. What you do is we could recreate this here, this little arrow here. So I recreated this arrow here, and I could recreate this arrow here. Okay, and then the exact distance and direction would be this little arrow here. And later on, we're going to put values to here and values to there. We can kind of calculate this. But then what we did is we kind of did this a whole bunch of times over and over again. I really came to realize, you know what? When I have this, I only really need to be concerned with the top half of this, or even the bottom half. We're really talking about a triangle. And over again, I realized that over and over again, what we're dealing with a lot of times is right triangles. This isn't necessarily a right triangle, but that's usually what it is. So we kind of came up with this method of called head to toe. In other words, the end or the head of the top of something to the bottom of something else, okay, or a new vector. Ooh, that was a bad line. Let me try that again. Sorry, guys. All right, here we go. So there we go. There's my line right there. So there's my new vector. Notice that these two vectors are probably identical to each other. If I was a better drawer, if I drew my lines much better, they would be really close to, or would be identical to each other in the same direction. So the triangle method is just saying, hey, it's just the top half of this parallelogram method, and they're similar. You just might see them both. This sometimes makes sense to people. I actually use this triangle method more often. I know it makes sense to say they're both starting at the same point because they're both being done at the same time. But in the end, you're going to get the same answer where if one goes first, like this a vector goes first, and then this one goes second as far as how you kind of think about it. All right. So we might have a boat, okay? And the boat, we know, is going at a 75-degree angle a little bit to the east, and it's moving at a rate of 60 miles per hour. Well, the boat's engine might be going faster than that. And this might represent the boat's engine right here. All right, so the boat's engine would be showing in Y. It's going straight north, and it's going actually faster than 60 miles an hour. We're not sure exactly yet how fast. And there's a current here that's pushing on the boat in an easterly direction. So it's pushing it more to the east. Now the boat's still making progress toward the north, but it's kind of slightly going to the east every minute or every kind of moment it moves because of that current. How can we figure out what's that current and what is how fast is the boat working? In other words, we want to know the impact of the horizontal and the vertical on this particular value. Well, we really just have to go back to the fact that we have a right triangle here. All right. And we're dealing with trigonometry. All right. So to find the x value here, we're going to just use the idea that the cosine of my reference angle, 73 degrees, is the adjacent angle, which is my x value, over the hypotenuse, which is 60. Which means that my x is just going to be 60 times the cosine of 73. All right, and I think it turns out to be, oh, I'm guessing here, I'm going to say like 17.3, 17.5, something like that. Now, when we're trying to find the y value, it's the sine of that reference angle, and then it equals the opposite side, which is my y value, over the hypotenuse. So now my y equals 60 times the sine of 73. If I got my graphing calculator, scientific calculator out, I'd find out that my answer here was 57.4. Okay, so now we're looking at this and we're saying, okay, I'm pushing on an object. At the same time, my friend is pushing on an object. And we know it's going to go in a different direction. So how do we show this visually, and then how do we calculate what's actually happening? So I am pushing on this object, and I'm pushing north. Okay? And my friend is pushing east, and I choose to do and just draw my friend pushing in the other direction here. I'm going to do it like this, one after another, like the triangular method. And I know that the object is kind of going to go like this. If you're like, oh, that doesn't make sense. I know you're pushing here at 20, and the friend's pushing at 13, and that's hard to see in direction. I understand. You could still think to yourself that, nope, I'm going to think of it differently. I know here's my object, and you're going to be pushing 20, or I'm pushing 20, and your friend is pushing 13, and then I know it's going to go in this direction. All right, which is fine. You could do it that way. We just have to copy down this, copy down your rectangle, and then you're actually just finding your here. You're finding this diagonal of your rectangle. Either way, you're still going to use Pythagorean theorem, okay? Because if this is 13 down here, this is 13 here, and really we just have the same little right triangle that we had here. So to find the length of this, which is my magnitude, I'm going to take my Pythagorean theorem. 13 squared plus 20 squared. All right, and when I add it up, there it equals 569, and I take the square root of 569, it's about 23.9. All right, so this distance is about 23.9. Okay, so now the next part says, like, what direction am I going in? Direction is usually given according to the horizontal, all right? So we want to go in reference to the horizontal is really kind of how we work that through, which means this. All right, here's kind of my thing. I have 13 here, I have 20 here. I could say at this angle or where this is. So it's really about how do I describe where this red line is here. I'm going to give it this angle right here. Say, okay, this is how far I go from my horizontal. My horizontal is whichever one looks like my x-axis here. So for that one, the tangent of my missing angle would equal 20 divided by 13, opposite over adjacent. To find that angle, you take the tangent inverse. You find the inverse of 20 over 13. When I did that, I got 57 degrees. So our answer here is actually 57 degrees south of west. All right? Meaning, if I have here my north, south, east, west, north, south, east, west, all right, this one technically is going here. All right, it's kind of like where am I in the world? Where if I saw this is my 0, 0, it's saying here, and this would be, you could say south of west, or just southwest. I don't care if you put south of west or southwest. Up here in the first quadrant is northwest, and the second quadrant is, or excuse me, northeast, sorry. Second quadrant northwest, southwest, southeast. Okay? So south of east, southeast. We usually just use our, since we're always taking it to our horizontal, it's going to be start with north, south, east, or west. All right. So a lot of different things use these vectors. We're going to see a lot of different examples. One is billiards. Most athletics use vectors. Flying, we're going to be talking about the air current, water current, and boats use vectors. So there's vectors used in a lot of different situations. I think it's going to be a fun week working on our vectors.